what is entropy. Yeah? So the entropy, okay, if you look at it, okay, entropy is defined as a measure of dispersal of energy at specific temperature. So it's a dispersal of energy. Okay, but if let's say you cannot understand, okay, what does it mean? Okay, so you feel that what is dispersal of energy? Okay, doesn't make sense. Okay, so if you want a better, I think, definition, okay, you can look at the measure of randomness, or okay, it's a measure of randomness or disorder of the system. Okay, so if I put it as an example, okay, if I'm going teaching two classes, okay, for example, JC2 Truth and JC2 Grace. And if I enter the class, JC2 Truth is, let's say, JC2 Truth, they are very naughty, for example. So when I enter the class, people are fighting with each other, okay, they don't want to sit in their places, and there are people pulling their hairs each other and so on. So very havoc, okay, very chaotic. Okay, but when I enter your class, okay, everyone is fully seated, okay, everyone is ready to learn, okay, so that you're very ordered. Now, when it comes to teaching, okay, I think better class will be JC2 Grace, because you're ready to learn. Unlike JC2 Truth, they are pulling their hair and actually trying to fight. But when it comes to chemistry, okay, it is going to be the other way around. Okay, for chemistry, okay, not chemistry lesson. For chemistry, okay, when it comes to reactions, we prefer them. Okay, we prefer atoms to be fighting with each other. We prefer atoms to be pulling each other's hair. Okay, we want them to be chaotic. Okay, we want them to be chaotic. So if I just want to rate them, okay, which one is better? Okay, so in chemistry, if you have more disorder, it will be rated better. So maybe I'll give you 90%. Okay, I give JC2 Truth 90%. But JC2 Grace, because they are very very ordered, follow instruction, I will just give 20%, for example. But this is for chemistry when it comes to reaction. The same applies to entropy. Okay, entropy is a measure of randomness and disorder. The more disordered you are, you will get a more positive value. Okay, the more disordered you are, you will get a more positive value of entropy. So that is important. Yeah, please take note. And then the rest is not so important. Yeah, so I'll just skip that part. You see, the system become energetically stable when become disordered. Okay, what example and so on. I think it's not important now when it comes to the new syllabus. Okay, but I think when you look at the system becoming energetically stable, I think you can make sense. Okay, when it become disordered, okay, it will be better. Okay, why? They can react with each other. Okay, they can react with each other, and they will become much more energetically stable later. Okay, so that is going to be the explanation for that statement. But if you don't want that also, so difficult, Mr. Gopi, remove it. Okay, don't bother. Okay, don't bother about it. Okay, what I want you to remember is, okay, entropy is a measure of disorder. Okay, it's a measure of disorder. So the next is, okay, this one also, when it comes to your syllabus, they didn't mention specifically that they want you to know about spontaneous change. But as a chemistry student, you need to know what is spontaneous change. Okay, a spontaneous change is actually a change that tends to happen naturally. And this change, okay, this spontaneous reaction, once started, they will continue to carry on. Okay, it will go on. Example, if you have methane gas and oxygen, once lighted, they will react spontaneously to form carbon dioxide and water. This is combustion. Yeah. But the question is, okay, I put it over there, why this reaction is considered spontaneous? Maybe Ashley, can you answer that? Okay, all the information are there. Why I can consider methane and oxygen reaction, okay, is spontaneous?
Because after once it lighted, the other reactions that follow, we didn't cause that, so it happens by itself. So it
Okay, so basically it's like this. I think once you provide the heat, okay, once you provide the heat to methane and oxygen, the moment they light up, okay, the moment they have that enough energy, you do not need to do anything. They will continue to burn. You do not need to actually just put your matchstick, okay, or whatever, just put over there, and then the moment you remove, they turn off. No, okay, it's like once started, you can remove it. It will just continue to light up. Okay, so the combustion will continue the moment, okay, once you actually start. But sometimes, okay, you do not need to even light up. Okay, sometimes the reaction is going to be very spontaneous, but that doesn't mean that the reaction like combustion, okay, is non-spontaneous. The reaction is spontaneous. It can be also where you start up initially. Okay, so example, okay, you can see that the example, okay, later before we go for example, it is very important to understand that spontaneous change, okay, so sometimes we think that spontaneous change must happen rapidly, must happen like something like explosion, okay, must be something very big. Oh, no need. You just think that spontaneous change can be also something that does not happen rapidly. Okay, it can be also slow. Okay, spontaneous change can be also slow, and sometimes it also needs input of energy. Okay, so sometimes it doesn't need. Okay, but even some reactions that need input of energy is also going to be considered as spontaneous change. Okay, so some areas of sometimes students have misconception. Okay, spontaneous change, oh, this is slow, so definitely non-spontaneous. Wrong. This one I need to light up. Okay, it doesn't happen. I mix, doesn't happen. So of course it's non-spontaneous. Wrong. Okay, it can be something that is slow as well. Okay, so if I just give you some example, okay, maybe I ask Davis. Okay, Davis, you see, if you have, we have learned about diffusion. Okay, diffusion. Imagine you have a hair gel. Okay, hair gel, colorless hair gel, and you put potassium manganate powder, okay, underneath. Okay, potassium manganate powder is like a black color, but when it starts to diffuse, they will change into something that is purple. Yeah. So if you put the potassium manganate, okay, under the let's say your hair gel, okay, in a container, after maybe 5 or 6 days, what you might be able to observe, Davis? I think simple science question. Okay, maybe even in primary also they learn about this. If you have, okay, potassium manganate, okay, and then you put gel, what will happen? You are muted, Davis.
Change color.
Okay, change color. Why is that, Davis?
The particles move.
I think simple answer, yeah, the particle moves. Simple answer is diffusion is happening. Yeah, because I think generally we think about diffusion is always happening like in gas. Okay, diffusion can still happen in gas, can still happen in liquid. It can still happen in solid. In this case, it is going to happen in solid. Okay, diffusion can still happen. Okay, now my question over here is this reaction that I mentioned just now, is it spontaneous? Actually,
Sorry, sir, can you say it again?
okay, just now, the same situation that I mentioned just now to Davis, okay, do you consider that reaction as spontaneous? Need to think. In order to do that, you need to think about what is spontaneous change.
Can you say what's the reaction again, sir? Sorry.
Okay, you missed the reaction then. The reaction is that having a hair gel and you put potassium manganate over there. So Davis mentioned that the potassium manganate, okay, they will disperse, they will dissolve, okay, diffuse, okay, that's the term, okay, diffuse, okay, and then the hair gel will start to become like purple in color, okay. do you consider that this reaction, which is diffusion in solid, okay, as something that is spontaneous change?
Sure. Why not?
Yeah, it is spontaneous. Okay, even though it is slow, it is spontaneous. So if you want to put it as how to consider which one is spontaneous and not, you just see the change that tend to happen naturally. Diffusion do happen naturally. Other examples that I can say that can happen naturally and can be slow is going to be rusting. Okay, if you have any metal, okay, even though you keep it for now, okay, this is made of metal and so on, you keep it for now, it is very shiny, but maybe 20 years or 30 years down the road, okay, with the proper ingredients of water and oxygen, okay, that metal will be rusted. Okay, so rusting also you cannot prevent. It is going to happen naturally. So it is spontaneous, even though it takes time. Okay, so if you look at these questions, okay, I don't want to spend a lot of time over here because it is in the previous textbook, it is in the new textbook, okay, but I do not very sure whether it is important because it's not mentioned in the syllabus. Yeah, so here, okay, which of the following changes are likely to be spontaneous? Sugar dissolving in water. The answer is spontaneous. Sugar will definitely dissolve in water. The smell from an open bottle, okay, of an aqueous ammonia diffusing throughout the room. Diffusion. It will happen naturally, okay, spontaneous. Water turning to ice at 10 degrees Celsius. Lindsay, do you think it's spontaneous? When
Yes.
normally water change into ice?
At 0 degrees.
Yeah, so this one is 10 degrees Celsius. Do you think it's spontaneous at that temperature?
No.
Yeah, the answer is non-spontaneous at that temperature. Okay, so at 10 degrees Celsius, you won't get water changing to ice spontaneously. But at 0, yes, okay, spontaneous reaction. Ethanol vaporizing at 20 degrees Celsius. Now, ethanol, okay, is going to be, it's easy to vaporize. Okay, it's easy to vaporize, okay, and you do not need to boil them. Okay, do remember, even though, okay, the boiling, I think when we boil water is 100 degrees Celsius. Ethanol, the boiling point is lower than that. I think it's about 70. Okay, but we are not talking about boiling. We are talking about vaporization. Vaporization can happen at any temperature. Okay, so ethanol vaporizing at 20 degrees Celsius, it is spontaneous. Even though you say water vaporizing at 20 degrees Celsius, the answer is correct. Okay, it is spontaneous. Water will vaporize at 20 degrees Celsius. Okay, water mixing completely with cooking oil. You do whatever also, they are not going to mix. Okay, so it's non-spontaneous. Limestone decomposing at room temperature. Okay, good luck with trying that. Definitely will not decompose at room temperature because we learn, okay, it's going to be thermal decomposition. The term thermal decomposition means it requires heat. Okay, so you need heat, okay, to decompose calcium carbonate to become calcium oxide and carbon dioxide. Without the heat, you are not going to get calcium oxide and carbon dioxide. So it's non-spontaneous. What is the reason and so on? You can just read over here. Okay, so any questions up to here? Dylan?
No, sir.
Raphael, any questions regarding spontaneous change?
No, sir.
Okay, let's continue. Okay, so now I introduced this term spontaneous. Okay, and now we actually just go back to our entropy values. Okay, what I want you to look is going to be this diagram, this table. Okay, the table tells us about the entropy changes, okay, of selected substances. Okay, you can see over here. Now, if you see general, okay, if you see over here in general, maybe can we come up with 4 conclusions? Okay, 4 conclusions based on this. I will guide you as well. Okay, 4 conclusions based on this. Now, roughly take a look at all these substances. Try to divide them into solid, liquid, and gas. What can you say generally, okay, when it comes to entropy of liquid? If you compare to, when it comes to entropy for solid, you compare with liquid and you compare with gas. Can you come up with a statement saying that they are going to increase or whether they are going to decrease, or I don't see any trend? Okay, please have a look. Newan, what is your conclusion?
Increasing.
Yeah. Okay. You if you just generally look, maybe in general, okay, we are not talking about everything. Okay, like for example, if you look at calcium, okay, it's 41.4. Okay, 41.4. If I have a look at water, it's going to be 69.9. And if I select one of the gas, 205, maybe oxygen, I can see that there is a general increase of entropy when it comes from solid, liquid to gas. Okay. If you ask me why, okay, this is going to be again coming back to the entropy. Entropy is the measure of disorder. Okay. So measure of disorder, if you look at solid, okay, how they are arranged with each other, they have regular arrangement. Liquid, okay, they are going to have some kind of less regular arrangement. Gas, they are not arranged regularly. They are just going to be spread just randomly, just like that. Okay, so you can see gas is more randomly arranged compared to liquid, compared to solid. That is the reason why you can see that the entropy increases from solid, liquid, and gas. So if I put over here, okay, you can see gases generally have higher entropy than liquid. Okay, liquids have a higher entropy than solid. Okay, but of course there are exceptions. Okay, what are the exceptions? Maybe if you look at calcium carbonate, then mercury. Okay, calcium carbonate, okay, 92.9. Mercury is 76. Okay, it's supposed to be mercury, supposed to be bigger. Okay, so there are some kind of exceptions. Okay, so therefore, okay, the trend is just a general trend. It's not applicable for everything. Okay, so you just need to remember the moment you see gas, yeah, entropy will be bigger. The moment you see liquid, okay, if you compare with solid, yeah, liquid will be bigger entropy than solid, something like that. Okay, another conclusion that I want you to derive is, let's say I compare, maybe let's compare carbon dioxide and carbon monoxide. Okay, carbon dioxide and carbon monoxide. If I ask you, between carbon dioxide and carbon monoxide, which one is more complex? Which one is more simple? Angela, carbon monoxide or carbon dioxide? Which one is simple? Which one is more complex?
Carbon dioxide.
Okay, carbon dioxide is complex, okay, because they have, okay, they are going to be having more atoms, okay, one carbon and two atoms of oxygen, okay. If you compare, okay, you see, if you have more atoms, okay, more complex molecule, if you, let's say, for example, okay, I give you a situation in a class of 100 students, and in a class of 20 students, which class do you think, okay, it will be more chaotic, Dylan?
The one with 100 students?
Correct. Okay, the one with 100 students will be more chaotic because there's a lot of randomness. Okay, so if you have a complex molecule, for example, CO2, if you compare with a CO2 has more atoms. Okay, so it's kind of a complex. If you have a complex molecule, okay, what will happen is the entropy will be greater. So you can see 213 compared to 197. Okay, of course, this is just a simple or random example I'm taking. Okay, but okay, I hope you get the idea. Like for example, if I compare within solid, okay, maybe calcium carbonate, I compare with calcium oxide. Okay, calcium carbonate and calcium oxide. Calcium carbonate is more complex. Okay, more atoms. Okay, so because of that, okay, even though they are same, solid and solid, calcium carbonate will have more entropy compared to calcium oxide. Okay, because they are complex. Okay, so this one leads to this. Okay, simpler substances with fewer atoms have lower entropy values. Okay, so this one you can read. Yeah, so next, okay, let's actually look at diamond and graphite. Okay, diamond and graphite. Now, both diamond and graphite, they are known as what? Okay, there is a term that we use which starts with A. Anyone wants to answer that?
Allotropes.
Yes, good. Okay, allotropes. Okay, both diamond and graphite, they are allotropes. They are built from the same material, which is going to be carbon, but different arrangement. Okay, so graphite is arranged in layers. Okay, diamond, there is going to be tetrahedral shape that is going to be continuous. Okay, now between diamond and graphite, which one is harder? This one?
Diamond.
Yes, diamond is harder. Now, always remember, harder substances, okay, harder substances, you can just think why they might be hard, okay, because they are going to be very much regular compared to another counterpart, which is going to be soft, okay. So you can just visualize the arrangement of a diamond compared to the arrangement of graphite. Okay, because of that, okay, diamond, okay, will have more regular arrangement. Therefore, the entropy, okay, because it's disordered, less disordered or more ordered, okay, more ordered. Because it is more ordered, okay, you are going to give them a lower rating, which is going to be the entropy is less. So you can see 2.4, okay, compared to 5.7. So harder material, okay, harder substances generally will have lower entropy. So that is going to be the third one that they mentioned in the textbook. Okay. So let's go for the fourth one. Okay, for the fourth, I think this diagram is not suitable. Okay, for the fourth. What will be suitable is going to be, maybe let's actually talk about water. Yeah, maybe let's talk about water. Water at okay, maybe I'll just show the slide that I prepared for the others tomorrow. Okay, have a look at this. Okay, now if you look at this thing over here, okay, if you look at ice, water, and steam, okay, all of them are water, okay, H2O. Okay, one is solid, water is liquid, steam is going to be gas. And if you look at the entropy is 48, 68, 188. Okay. So what can you say, okay, with the state and the entropy? Maybe this one I'll ask someone, maybe Jonathan, can you tell what the conclusion that you can arrive, okay, with this entropy?
The solid state has the lowest entropy, then the gas state has the highest.
Okay, that is going to be something similar to number one, right? The first statement. But if let's say ice becomes water, when ice becomes water, when I provide heat, right? Okay, I provide heat, and then they are going to reach their melting point, and then they become water. And then after that, I keep on providing heat, and then they will reach their boiling point, then they will become steam, they will become gas. So what can you say as you keep on providing heat or temperature increases? So let's say statement, as the temperature increases, what will happen to the entropy value? Jonathan? Yeah. Maybe whoever who's answering, just answer.
As temperature increases, their entropy value also increase?
Yes, correct. Okay. So as temperature increases, the entropy value will also increase. Okay. So I'll share from here. Okay. So that is very important. Okay. Because, okay, you can tell, okay, because when you look at the definition in the beginning, they mention, okay, that entropy is going to be a measure of dispersal of energy. Maybe just now I say if you cannot understand, okay, we just follow the randomness or disorder of the system. But now, okay, you can come back and then relate to this dispersal of energy. Okay, when I am, okay, ordered, okay, let's say I'm in JC2 Grace, I just sit down and I just don't move anywhere. I'm ordered. Okay, but as I receive the heat, okay, as I receive the energy, I start to become naughtier. I start to move around. I start to actually maybe look at my neighbor and then suddenly start to actually pull the neighbor's hair, start fighting and so on. So it become more chaotic. Okay, I become more chaotic. Why that thing is happening? Because I'm having the input of energy, and this energy is coming from temperature. Okay, it's coming from the heat, and this is going to be not only affecting me, it will also affect my neighbor, it will also affect his neighbor, and it will also affect the other neighbor as well. So overall, that energy will be dispersed. Okay, so similar if you have a solid, and that solid, okay, when it becomes liquid, generally we are expecting the entropy to become greater. It will actually increase gradually, okay, gradually. But what you need to notice is not gradually all the time. Okay, not gradually all the time. When I mention gradually, so let's look at solid to liquid. When I mention gradually, this is gradually, this is gradually, this is gradually. Okay, but what can you notice? I think this one is also primary work, or maybe if you want to refer to Sec 2 or your Sec 1, okay, when you learn science, okay, you will notice that there is a sharp increase, okay, at that certain temperature, okay, at this temperature. Okay, so if I erase this, okay, you can see that, okay, there is going to be a sharp increase over here. Why there is a sharp increase over here? Because that's your melting point, and that is going to be your boiling point. So all of a sudden, okay, the entropy will suddenly increase. If you cannot remember this, okay, just now, remember I was showing you the data, okay, for maybe I'll just get the data and then just put over here. When ice, okay, it was 48. And when water is going to be 68. And when steam is going to be 188. Roughly, okay, if I put it over here, okay, just take it as this is going to be 48. Okay, and this is 68. Okay, and then maybe this one is going to be 188. You can see there is a big jump. Okay, you can see there is a big jump over there. So when you look at this, okay, they are going to have a big jump whenever there is going to be a change of state. Okay, change of state. Okay, but whenever within, let's say, for example, it is solid, okay, and I'm heating them up. Okay, I'm keep on heating them up. Okay, and what I am going to expect to see, I might actually see a gradual increase. Okay, I will see a gradual increase. I will see a gradual increase. Why is that? Okay, if it is, especially if you are looking into solid to liquid. Okay, solid to liquid. So it means solid to liquid. I think this one. Okay, from I think this part, I think everyone should know is a transition between solid and liquid. Okay, so this one is solid. Okay, this one is completely liquid. Okay, so if I have this, okay, what is happening? Regular arrangement changes to irregular arrangement. Okay, and what happens? Okay, they start to rotate and slide over. So it's like something like they keep on moving, rotating, and slide over, like something like a flowing, yeah, like water. Okay, they are flowing. So that is going to be solid to liquid. what happens next? Yeah,
Sir, the sliding and rotating.
it's
When
happening
does
for
that
the
begin to
solid.
occur?
Solid. So it means it's within here. Okay, it can also happen here, and it is also happening over here. So I put the 2 star over there. Yeah. So it
Okay.
means from solid and even during the transition. Okay, and also during the transition also it happens. Okay, so that's flowing will be more. Yeah, rotating and sliding over will be more. Okay, so if you look at liquid to vapor, okay, so this one is going to be liquid and this is vapor. Okay, so this thing and here what happens is you are starting to be able to free to move around rapidly. Okay, because they are far apart. So it means they started to become gas. Okay, they started to become gas. So if they ask you what happens and so on, okay, you need to know. And if they ask you to draw or sketch, okay, please remember, I think sometimes be careful when they ask you to sketch. This is entropy and temperature. Generally, they will go up. Okay, so you need to know what is going to be your melting point, okay, and what is going to be your boiling point. So roughly, okay, if you look at the melting point, okay, what is going to be the melting point, okay, let's just simply talk about boiling point, for example, because I think that is going to be more I think there are some questions in past year paper that they have asked before. Okay, the boiling point, okay, is supposed to be 100 degrees Celsius. Yes, Josh.
It's like the rapid increase of the entropy as it like from the boiling point because the temperature stays the same and also because the gas has higher entropy than the liquid.
It's like this, Josh. Okay, remember like last time I think you have learned this diagram. Temperature, okay, increase, and then suddenly there is no increase in temperature. Okay, and then after that the temperature will go up, then something like this. Okay, so it's similar to that. Okay, so it means that why temperature is increased because the it is going to gain energy to break the bond and so on. Okay, so similar. Okay, they are breaking the bond, so the entropy is increasing because it's getting more disordered. Okay, but from here to here it means like they are like, just imagine like yesterday only you saw a boy, he's very well behaved, but tomorrow suddenly he become very naughty. Okay, so out of sudden, similar to that, it means that now all the bond is completely broken, they become super naughty. So there is a sudden increase of the entropy because of that. So it means the entropy here, okay, it because they already changed. Okay, they already changed from solid to completely liquid. They already changed, okay, from liquid completely to become gas. So there is going to be a sudden increase of the entropy over there. Okay, so similar to this diagram also. Okay, what happens here? Okay, because now the energy is being used, okay, to break the bond, okay, within themselves itself, so that they can break free or something like that. So please refer to the old concept that you have learned. Okay, but it's a similar concept. Now, what I want to mention over here is sometimes they'll ask you to sketch entropy graph. When you sketch entropy graph, okay, you need to be very careful because it's Kelvin over here. Kelvin is going to be 273. Okay, so when you put over here, you must be very sure it's supposed to be 373. Don't go and put at 100. Okay, so it's supposed to be at 373. So there is a question later also, I think tomorrow I will discuss. They'll ask you to sketch and then you need to write down and then how it will change and so on. So this one we will look at it later. Okay, now let's look at explaining differences of entropy. Okay, now if I have, okay, Br2, okay, the entropy is going to be 151 and the entropy is 116. Okay, why Br2 has a higher entropy? So maybe someone can answer this. Kenneth, can you answer why?
Is it because it's higher?
Is it because of?
It's higher in the group chat.
Because I think the simple thing is to answer because they are liquid. Okay, because they are liquid. Okay, if you compare with solid, okay, so liquid is going to be more disordered. Okay, so they will have higher entropy. Okay, so always compare the state first. Okay, like for example, for B, you see they are gas and gas. You cannot compare the state. So now you have to consider about other factors. Okay, H2 and CH4. Okay, what can you say? CH4 is more complex. Okay, so it has more atoms. Okay, therefore, okay, I do expect the entropy to be greater. Okay, similar here, this is liquid and this is solid. Okay, so liquid should be having something that is greater, okay, more disordered. And if you look at SO2 and SO3, you see gas and liquid. Okay, gas and liquid. So generally, liquid supposed to gas supposed to have a higher entropy, so they have higher entropy. But some of you might actually ask, SO2, SO3. SO3 looks like more complicated, more complex. Okay, why? Why that is not higher? Okay, then you just need to mention. Okay, now first we look at the state. Okay, gas. Okay, definitely they will have more degree of randomness compared to liquid. Okay, so if they are in the same state and so on, then you look into the more complex or not. Yeah, something like that. So whatever it is, okay, you can see here, okay, all the explanation they are given here. Okay, maybe when later I pass you this, okay, you can just go through all this. Yeah, so I will move on. Okay, now how about entropy in reactions? This is generally I'm comparing between Br2 and I2. I'm comparing H2 and CH4. Okay, but how about within the reaction itself? Okay, now if you look at within the reaction itself, okay, if you have more gas molecules, okay, have a look over here. If you have more gas molecules, there are greater number of ways to arrange them. Okay, so why gas molecule? Because then only you can arrange them. You have more disorder. So you don't look at solid. Try to ignore the solid. Okay, try to focus on gas. So if you look at this example, okay, ignore. There's going to be 1 mole of gas on the product. So there is 0 over here, no gas. There's 1 mole of gas. So what does it mean? Product is more, okay, disordered. Okay, product is more disordered. So therefore, okay, we can say that the entropy of the products, okay, they are bigger, okay, or more positive. Okay, so something like that. So if you look at the second example, you see all of them are gas. All of them are gas. But what you need to do, you look at the number of moles. 2, number of moles. 5. So 5 is more than 2. It means that, okay, it means that your product, okay, will have a greater entropy compared to the reactant. So it means the entropy of the product will be greater. Something like that. Yeah. So if it is going to be, this is going to be the greater number of ways of arranging them and higher entropy. So if it is decrease in entropy, can we look at that example? You can see here. Okay, gas. Okay, so 1 and 3 is 4 and this is 2. You can see from 4 to become 2, okay, less number of molecules. Okay, so it means less arrangement. Okay, so the degree of arrangement will be lesser. So if it is lesser, okay, so we can say that the entropy of the product, okay, is less than the entropy of the reactant. That is what they want you to identify. Okay, so now, okay, there are some questions here. Okay, so what can we say? Okay, of course, I don't want to go through everything. They say here, suggest whether the reactant or the products will be greater. Which one will be greater? Reactant or the products, the entropy? Or whether it's difficult to decide and explain. Okay, so you can see here, I told you to look at gas. No gas on the product. Okay, so you have 2 moles of gas, 0 at the product. So you can say that the entropy, okay, at the reactant is more compared to the product. Okay, and then let's try another example for B. You see, look at the gas, 1 mole, 1 mole. If it is same, the answer is difficult to decide. Okay, the answer is difficult to decide. There will be other factors that will come in where you can read over here. Yeah. So if you look at C, okay, you can see gas and no gas here. So 1 and 0, I can say generally, I can come up with a conclusion. My reactant, okay, my reactants will have a higher entropy compared to the products and so on. Yeah. So any questions on this part? This one you can actually just go through here. Plus with the explanation, it's all given over there. You can just go through. Yeah. So now, okay, I will go into the reason why I was rushing, okay, is because I want to teach the calculation today, yeah, because I don't want tomorrow when I teach, I start from the beginning. No, I don't want, yeah. So here, okay, calculating entropy changes, okay, you can see that, okay, this one, okay, what we do, ignore, okay, ignore, okay, I don't want to discuss about this. Okay, it's not in your syllabus anymore. This one also, ignore. Last time we used to have this. Okay, they removed this. Okay, it's much more better now. I think more easier for you. Yeah, more easier for you. Now, I want you to remember this. Okay, this is the formula, the only calculation that you need for now. Okay, which is the entropy of the system. Okay, or if you want to forget the system also, it's okay. Just think about entropy. Yeah. The entropy is going to be entropy of the product minus the reactant. Okay, so do remember one thing, how to calculate entropy, product minus the reactant. And we need to take into account like stoichiometry, like what we do for the calculation in enthalpy. I'll show you some examples. Okay, but the formula is entropy of the products minus the reactant. So let's actually look at into how to do use that. Okay. Calculate the entropy change of the system of the following reaction. Okay, all these information are given. So how to do? Okay, very simple. Okay, you just need to calculate. Okay, you see the entropy is going to be product, entropy of the product minus entropy of the reactant. So what is entropy of my product? This is my product. So this is going to be entropy of my product, which is going to be 39.70. That's going to be my product, but it's 2 moles. Okay, it's 2 moles. So I need to times that by 2. So I just put over here times by 2. And then I minus the reactant, 2 moles of calcium. This is calcium. Okay, I put 41.40. Okay, times 2. Okay, plus oxygen. This is oxygen, 205. Okay, and then I can get the value. Okay, you can just have a look over here. Okay, the same, 2 times this. Okay, and then you minus. Okay, you minus with this. If you calculate, you will get this negative 208.4. Okay, last time we used to learn this. Now ignore it. Okay, later. That's why I told you I don't give it now. Later, after I remove all this, I will give you. Yeah. So for now, okay, you just need that. Yeah. The rest has been removed from your syllabus. Okay, let's move on. Okay, another example. Okay, calculate the enthalpy change of the system of the following reaction. Okay, so you can see here. Okay, your formula is S system equals to S product minus S reactant. S product, carbon dioxide 213.6 plus, okay, 2 times water. Water is going to be 188.7, close the bracket, minus the reactant, CH4, 186.2, 202. So I need to times by 2. So 2 times 205, close the bracket. Okay. Once you do that, you will get a value. Okay. If you compare now with the working, 213.6, 2 times this, then close the bracket. Okay. Minus this one. Okay. And then plus 205 times 2. And you will get negative 5.2. Ignore this. Okay, quite simple. Okay, I'm very sure you can do this. Here, okay, there are some examples over here where you can also try. Okay, maybe, okay, I'll just go through one of it. Okay, not everything. Okay, so maybe I'll just go through this one. It's the same thing. Okay, you can just go through also. Okay, so this one O2. Okay, O2, you just look at O2 here. Okay, the entropy is all given here, 205. So it's supposed to be enthalpy of 205. So I just put here 205. And then 2 times water. So water is going to be 69.90, 2 times. Okay, so bracket. And you minus the reactant, which is going to be 2 times H2O2. So you look for H2O2, 109.6. So you have that. Once you minus, you will get a positive 125.6. Okay, and so on. I'm very sure you can do the rest as well. Okay, quite simple. Okay, quite simple. They have removed this as well. Okay, they have removed this. They have removed this. So many things that they have removed. Okay, they have removed a lot. Okay, even this one. Okay, that's why I told you my suggestion is, okay, even though they have removed this, okay, in the new textbook, I think something wrong with the new textbook, the one that I feel, yeah, this is my personal opinion only, yeah. It's the same author, okay, 2 authors, okay, but I think because of the removal of the there's a change of the syllabus. I think they were rushing to publish the book also, yeah, and plus with the pandemic and so on. So what happened? Okay, the quality of the book is not so good. Okay, so what I feel that the book was rushed. Okay, they referred to the syllabus. Okay, but they didn't change the order of the the content. Okay, and also, even though they have removed the part of the syllabus, you know what they do in the book? They just say this part is not tested in your syllabus. But it's good. Okay, it's good to know about this. Okay, so that you can understand things better. They put a statement, and after they put the statement, they go and give 6 examples of that question. Okay, yes, as a student, okay, generally you will get confused, okay, because they already put it's not tested, and why you give 6 examples of that question. Okay, so now, okay, my suggestion is like this. Okay, this one I'll stop share and I will share here. Okay, my suggestion is you go, okay, you go and refer to the site, okay, or you go. Are you guys still with me? Wait, yeah.
Hello, sir. You okay?
Disconnected. Okay. I think something wrong with the Zoom for a while. Yeah. Can you see my screen?
No.
No, yeah. So hold on. Okay, something wrong. Can you guys see my screen now?
Yeah, we can.
Okay. So you see, okay, this is my suggestion now. Okay. If you want to use the new textbook to double check, go ahead. Okay. And I'm very sure that you have the old textbook, the hard copy of the textbook. Okay. I think having a hard copy of the textbook is really good. Okay. What I want you to do is, okay, I will do my part. I will refer to the syllabus and I will put the content of the syllabus, okay, part by part here. Okay. And you can double check, okay, when before you study and so on, you can double check, okay, what are the things that you need to cover, okay, what are the things that you need to cover, okay. And if you study the entropy change now, okay, as we are studying over here, you can see we need to know the term entropy. We need to predict the sign, okay, when there is a change of state. We have done this. We also have done during temperature change, okay, there is a gradual increase, and then during the melting point and boiling point, what will happen and so on. I gave you the example. During a change in the number of gases molecules, we have already done also just now. and calculate the enthalpy change, which is going to be the product minus the reactant. Can you see this part, the last part? The use of surrounding and system is not required. Now, even though they put over here, okay, your new textbook, they still didn't remove it. They put over there, okay, this is not required, but they still put the examples over there. So I want you, okay, when you use the old textbook is better, because now if new textbook, you have to refer from your PC, you have to refer from iPad, then so many things you need to refer. If you have your textbook, I will suggest have your textbook and you refer to, if whatever that I taught is still fresh in your mind, then you can cancel the part that is not required. But let's say you didn't study immediately after my teaching and so on. Okay, so what you can do is to refer over here, and then you can just cancel the part, okay, that is not included over there. Okay, like for example, the equation of the enthalpy of surrounding and so on, you just cancel. Yeah, you can just cancel over there yourself. Okay, but that's why I told you, maybe sometimes to cancel, maybe you get confused which one to cancel and so on. Okay, nothing can be helped, because you see the old syllabus contains the same thing that is not required. The new book also contains something that is not required. Okay, there is no other option. You have to do something. Someone have to do something. Okay, so you need to do the additional step, which is going to compare. Okay, so that is the additional work that you need to do. Okay, and as teacher, I will guide you. Okay, this one not involved. Okay, if that's why sometimes I'll put the new like for example this one I shared over here. If you want to study, okay, today, you can go and study using the lecture 2, which is going to be tomorrow. I will discuss this in class also. Okay, so this one I have modified. Okay, I've modified based on your syllabus. Okay, so the one that I present just now is not modified yet. Okay, it's not modified yet. So I will present this tomorrow, okay, in the lecture. But you guys, okay, immediately after the lecture is your lesson. So I will go through it again. Okay, I will go through it again. Why I don't want to discuss this slide? Because I want to still introduce you guys to this before I go through this question. Example of past year question. Example of this question. I want to still let you, learn first rather than rushing into stuff. Okay. But some of the things are there. I have removed some of the questions. Okay. But you can notice that this one is important. Okay. But the one that is not important, I have removed it. Okay. So you can refer to this, okay, to study. Yeah. Of course, I don't provide notes. Okay. If you ask me, Mr. Gopi, do you provide notes? No. As I told you, okay, I will not provide notes. If the maximum you are going to get from me is going to be something like this. Okay, you write on your own. Okay, or sometimes I do provide like whatever that I write. Okay, it will be also here, maybe like notes. Okay, for example, like this, it's all the one that I scribble. Okay, so you can just go through that. Okay, the scribbled notes and so on. If I put over there. Okay, but I want you to, if you download the lecture part and then you scribble over there, it's already good enough. Now, be careful, okay, when you download notes from Z-Notes, okay, when you use notes from different classes, okay, be careful. The new syllabus is different than the old syllabus. All those contents, the unnecessary contents, will be still there. I can guarantee you 97% unnecessary contents will be there. Okay, so it's better, okay, for you to filter the information and create your own. Yeah, so this thing is going to help you. Okay, so be careful. Okay, so I tell you in advance. Okay, because I don't want you to end up studying something and at the end of the day getting too many information and too confused. Okay. And at the same time, do remember the syllabus is created so that it's easier for you. So no point, okay, in going and learning everything like the old syllabus, and at the end, they are not testing on it. Okay, so be careful. If you're using the new textbook, okay, please be careful. If you're using the old textbook, be smart. okay, follow the syllabus and then compare. Okay, but if you really want, okay, normally if you have the notes and so on before the class and so on, check the Google site. Okay, is there any updates? Okay, is there any updates, and download that. Okay, because nowadays I'm trying to avoid, okay, sharing everything to the WhatsApp group. I will slowly move that. Okay, I will just say refer to the Google site and so on. Okay, so that I don't end up uploading at multiple places. Okay, because currently I need to upload in AIS, I need to upload in the portal, I need to upload in WhatsApp. Okay, I need to also send to different groups and also teachers from different campus. Okay, too many things. I don't want to. It's much more better I create one and just put it in one place. Okay, people just go and get it done. Yeah, but it is important. Materials will be there. Okay, but it depends on you on how you want to use those materials. Okay, all the videos and everything is there. Okay, too many information if you look at it. Okay, too many information even from last year. Okay, the content from last year, the previous year, everything is there. Okay, so it's just whether you want to learn or not, whether you want to go and spend the time to explore the material. Okay, so you just can go and see which one. Okay, which one is suitable. I told you. Okay, if you are advanced student and you just want to just do a review, go and look for the one that is going to be shorter duration. If you really want to, you miss out everything, you just want to go through everything, then go for the full lesson. Okay, you can just select which one you want. Yeah, I don't want to keep on wasting your time. Okay, but okay, I think I have done with what I wanted to teach today. Okay, but if you still confused, yeah, tomorrow I will go through the hydration solution and also all this plus with some revision questions. And Friday we will do some selected revision questions also. Yeah, that's all for today, guys. Okay, see you. Bye.
Thank you, sir. Bye, sir.